Hello all, today the topic we are going to discuss is vehicular ad hoc networks. These are the contents I will be covering today. First I will give the basic overview of VANET, then we will discuss some routing protocols and compare their performance, and then the applications at the end. The main focus will be on routing protocols. So first, the introduction. VANET is very similar to MANET. And those who don't know about MANET stands for Mobile Ad Hoc Network, in which mobile nodes are communicating with each other. But in VANET, vehicles are acting as nodes and communicating with each other. So in these modern times, vehicles are everywhere and almost everyone uses vehicles. And the biggest problem with them is their safety. Many of us has seen many accidents involving vehicles. So what we are trying to do here is to create a safe environment for vehicles by allowing vehicle to vehicle and vehicle to roadside communications in VANET. Through this communication, cars can share vital information and warnings which can save the life of a person. By allowing this communication, we are trying to reduce road accidents and increase passengers' comfort. So as I said, the main aim of VANET is to provide an accident-free environment and move toward implementation of zero accident car by the help of vehicular area network. Thousands of people die yearly in every country. In Pakistan alone, more than 5,000 people died in 2020. So VANET is trying to reduce those numbers and save as many lives as it can. And now the VANET architecture. There are three main components in VANET. First one is onboard unit or OBU. OBU is present in a vehicle which allows the connectivity. It is equipped with different communication modules. So the communication to a vehicle is possible through onboard unit. OBU is responsible for all mobility and networking function. Second one is application unit. Application unit is also present on a vehicle. The application unit can be a dedicated device for safety applications or normal device such as personal digital assistant. So basically OBU provide communication and application unit decides what to do with the information coming from that communication. Third one is roadside unit. As the name suggests, it is present on the roadsides and it provides different functionality. Here's a simple overview. Here you can see that both OBU and application unit is present on a vehicle and these vehicles can communicate with each other or with RSU through which it can connect to other networks such as internet. RSU can be used for many functions, but the main functions of RSU is to extend the range of ad hoc network. For example, if this vehicle is out of the range of this vehicle, then through RSU they can communicate with each other. Or RSU can share warnings to vehicles like low bridge warnings or accident ahead warning to warn the driver in advance. Or if certain applications need internet connectivity, then RSU can connect OBU with internet. Communication domains or the type of communications. There are three main domains. First one is in-vehicle domain. This is the communication between OBU and application unit happening within the vehicles. Second one is ad hoc domain. It involves OBU and RSU. It is further divided into two types. First is the communication between two vehicles happening through their OBUs. And the second one is the communication between the RSU and the vehicles. Third domain is infrastructure domain, in which OBU communicates with RSU to connect to internet or other networks. Here you can see different domains. Here you can see that the communication between OBU and application unit is in-vehicle domain and the communication between two vehicles is ad hoc domain. And when the OBU connect to internet through RSU, this domain is infrastructure domain. Next is characteristics of VANET. Now these characteristics are very important because routing protocols are defined based on these characteristics and properties. In VANET, we make assumptions that mobility is random, but the movement of vehicles is restricted to roads and movement can be two-sided. So in VANET, we can predict the mobility of vehicles. The scale of a network here is very huge. There can be thousands of vehicles acting as nodes. This is beyond the scope of VANET and its protocols. Although the network is very large, the density can still vary a lot, as we generally see that during office time traffic becomes quite dense, but at night there is no traffic and congestion. So it is very important to consider variable density while defining protocols. Now here is another major difference between MANET and VANET. In MANET, while defining protocols, energy efficiency is a huge factor because power of nodes is very limited due to the small size of nodes. But in VANET, there is no power constraint because car can be equipped with huge batteries. VANET is a very dynamic network. Velocity of vehicles is in the range of 20 km to 60 or 80 km per hour, which makes the network highly dynamic. Again, due to the size of car, they can be equipped with sufficient number of sensors and computational resources such as processor, memory capacity, advanced antenna technology or GPS system, which can improve communication a lot. VANET has to be very secure and private because security is a major concern here because drivers' life depend upon it. And now the routing protocols. Like I said before, VANET is highly dynamic. Although the mobility of a single vehicle can be predicted, the overall network is still quite unpredictable due to variable traffic density and vehicle speeds. This can result in drop of information which leads to a poor communication. So we need a very robust protocols for the VANET which can deliver a packet with a minimum delay in second. Routing protocols can be divided into many categories. Based on how they forward the data, they can be topology based or geographic based, or they can be unicast, multicast, broadcast, or if they are traffic security aware or non-aware, or what kind of traffic they are dealing with. But the major categories of protocols are topology based, in which protocol use routing table which contain the information about neighbor node to router data, or the geographical routing, in which we use the actual physical location of a vehicle for routing. These protocols need extra resources, which is GPS of course. And the cluster base, in which cluster of vehicle is formed and supervised by a single vehicle within that cluster. Among them, geographic based protocols perform the best, which raises a question that why they perform best. Like I said, that vanity is extremely dynamic. So in protocols like topology based, the information of routing tables can become outdated pretty quickly, due to which packet can be sent in wrong direction and create large overhead and delay. While in geographic based, we are always checking the position of a destination, so the packet can be delivered to its precise location rather quickly. And since geographic based protocols perform best, we will study only this type. The first protocol we are going to study is ISR, or Improved Road Segment Based Geographical Routing Protocol. In this protocol, we divide the road in segments for routing, and it is designed for urban areas. While routing, we consider these parameters, which include vehicular node position, information, direction, traffic density, and link quality between the communication nodes in a network. Each segment includes head node, which initiate routing based on these parameters. Now first we'll see how the segments are formed. When a source node and destination nodes are within each other's range, they can directly communicate with each other. But when destination node is out of the range of source vehicle, it divides the road into segments. Like I said, for geographic protocol to work, every node and vehicle has to be equipped with GPS and the complete map of area. Segments are formed by the presence of intersections and the road trajectories. So the segment is formed between two intersections. So here this road is one segment and this is another segment. Here you can see that this is a source node and this one is a destination node, which is out of the range of source node. And since it is out of its range, the source node will divide the further road into segments, and these two segments will be formed. Now the source node has to decide that which segment will receive a data based on the parameters I mentioned earlier. Let's say that this segment is selected. The source node will then transfer a data to this head node. Now this head node will become a source node, and it will transfer a data further to this head node. And by continuing this process, the data can be transferred to a destination node. And now we will see the head node selection. Like I said, head node performs routing within segment and between segments. After segment is formed, we select vehicle for head node. Every vehicle shares the information of its position, direction, and link quality and neighbor node within the segment. Then the protocol checks the position and the direction of vehicles. Then after that, the protocol calculates the score for selecting the head node. Scores are calculated on three metrics. First metric is position. Vehicle has to be at the center or close to the center. Second one is direction. Vehicle's direction should be toward the destination node. And when there is a tie between score, we call third metric or parameter, which is the link quality. And these are the equations that is used for the head node scores. Here's a flowchart for head node selection. First we check the vehicle direction and position, and if the direction is toward destination and is in center, then we will check that if only one node satisfy this criteria, and if the direction is not toward the destination and it is not centered, then we will check other vehicles. And if only single node satisfy the criteria, we select it as head node, and if not, then we will select the node with the best link quality, and we will select this node as a head node. And after that head node is selected, we will check if head node is present within a segment. If yes, then we will select this head node to forward the data, mean the head node is selected successfully. If not, then we will again check the other vehicle's direction and position. This part is when the head node leaves the segment. Here's a flowchart for the routing process. First, we get the distance and direction of a node, and and if destination is found, meaning that the destination node is in the range of source node, then we can directly forward data to the destination. If not, then we divide the further road into segments, and we add that segment into a path. After the segment formation, we select the head node we select the head node. And after selecting the head node, we will check that if the head node is connected to the next head node, and if they are connected, then we can select the head node to forward the data to the next segment. And if the destination is found in that segment, then we can directly forward data to that destination. If not, then we will continue and then we will add another segment, and this process will be continued until the destination is found and the data is forwarded. And when the data is forwarded successfully, then the protocol ends. Next protocol is TASR, or Traffic Aware Segment Based Routing Protocol. Segments are also used in this protocol. Here routing is based on traffic density. TASR look for next and next to next segment. In ISR we only look for very next segment, but here we are also looking for the next to next segment. So TSR employs look ahead depth of two segments for data packet routing, while in ISR we only employ a look ahead depth of one segment. Here are some characteristics of TSR. Just like in ISR, segments here are also formed depending upon intersection. There are two head nodes in segment at the opposite end. Head node contains the information which includes segment ID, transmission time, accessible transmission range, and overall vehicular density on a segment. Head node performs a routing based on a parameter called estimated connectivity degree or ECD. Each node has info about its neighbor which it has to update regularly. TSR uses route request and route reply to make route between source and destination node. It also receives acknowledgement after sending a data. When a destination node receives a route request, it sends back route reply indicating that link is established. In case source does not receive route reply, it sends route request again. Since it is a geographic based protocol, source knows in which direction destination node is. In case communication link breaks during communication, the route error message is sent to source so it can send route request again. It also uses request to send and clear to send frames to mitigate the terminal problems in wireless communication. To control large overhead, the protocol does not broadcast the data to entire region, but source only broadcasts data to an area which contains the destination node. Here is an overview of TSR. Here you can see that between two intersections there is one segment and each segment contains two head nodes at the opposite end. This one is a source node and this is a destination node, and you can see that destination node is out of the range of source node. So the source node will divide the further road into segments and will transfer data to a best segment with based on a parameter I mentioned earlier, which is ECD. And let's say that this head node receives data, and then when this head node will receive data, it will transfer data to the head node at the end through intermediate nodes or vehicles, and then this head node will again transfer data based on ECD, and the process will be continued until the data reaches to into a segment in which contain the destination node. Remember how I said earlier that the mobility of a vehicle can be predicted. The protocol predicts that when the data reaches to these segments, the destination node will be at in this segment. So it has to route the data to this segment. And let's say if somehow at intersection the destination node changes its direction to this segment, then the meeting point will also be changed, and that's the protocol will know that now it has to route the data to this segment, and this is why the geographic protocols perform better than others. Here currently this one is a source node and this one is a destination node. Before sending a data, it will send a request to send, and if everything is alright and they are connected, destination will send back a clear to send. After that, source will transfer a data, and when the destination receives the data, it will send back acknowledgement that data is transferred successfully. Now this one will become a source node and this one become a destination node, and this process will be continued until it reaches its final destination. Third and the last one is VBRP, or Virtual Backbone Routing Protocol. This protocol uses RSU to make routing decisions. Transmission is depending upon backbone nodes, which are also like head nodes. Backbone nodes are selected based on link stability and the node mobility. For this protocol, RSU has to be present in communication network. For previous protocol, RSU could be present in network as nodes, but their presence were not conditional. This assumption limits the protocol to infrastructure-based scenarios where an RSU is always present. Protocol can be mainly divided into two parts: packet forwarding within the road segment and forwarding path selection at intersection. In this protocol, packet transmission mainly relies on backbone node. When a backbone node receives a packet in road segment, it transmits the packet to its neighbor backbone node toward the end side of a road. The packet is transmitted through backbone nodes until it reaches the intersection. At the intersection, the packet is received by RSU, and then the RSU make decision that which segment will receive a packet next based on the performance of route segment. And when the data is transferred to the backbone node in that segment, the communication again happens through backbone nodes until that it reaches its final destination. Here you can see that this one is a source node and this one is a destination node which is out of its range. So the source node will transfer data to that backbone node, and that backbone node will transfer data next to this backbone node. Now this backbone node is at intersection, so this will transfer data to RSU. Now RSU will decide that which segment will receive a data based on their performance and the presence of source node. Now this segment contains source node and destination node, so that RSU will transfer data to this backbone node, and then this can transfer data to this backbone node, and then the data can be transferred to the final destination. So here you can see that why we need RSU, because at the intersection the decision is made through RSU. So RSU is a must for this protocol, which limit its ability. Here's an overview and the comparison of the protocols we have studied so far. We have studied three protocols: ISR, TSR, and VBRP. ISR was proposed in 2020, TSR in 2018, and VBRP is also proposed in 2018. All of them is urban based and geographic based protocols. ISR uses node position, direction, traffic density, and link quality, while TSR uses only traffic density, while VBRP uses link stability and node mobility for routing and the selection of head node. In ISR, only single head node is present at the center, while in TSR, two head nodes are present at the opposite end of a segment, while in VBRP, multiple backbone nodes and RSU can be present anywhere within a segment. And now we will see the performance of all the protocols we have studied. Simulation results are taken from this research paper. The author in this paper selected Chicago City for the simulation. Simulation is performed in NS2. These are the simulation parameters. And number of vehicles is varied from 100 to 350, and the transmission range of each vehicle is 300 meter, while the vehicle speed is also varied from 10 to 100 kilometer. First analysis is made on number of nodes. As number of node increases, packet delivery ratio increases too. This is because when the traffic becomes congested, more and more vehicles comes in each other range. So the packet delivery ratio increases. But among the protocols we have studied, ISR has the highest delivery ratio, while the VBPR has the lowest. And same goes for end-to-end delay. As number of nodes increases, end-to-end delay increases. But ISR has the lowest end-to-end delay. And like I said earlier, that the efficient protocol has the lowest end-to-end delay. Second analysis was made based on speed of vehicle. As speed of vehicle increases, the packet delivery ratio decreases, but ISR still has highest delivery ratio. And with the increase of speed of vehicle, end-to-end delay increases, but still ISR remained ISR remained its lowest end-to-end delay. So we can see that ISR is the best performing, while VBPR is the worst performing protocol, and TSR is in between. ISR is the best performing in both number of node analysis and vehicle speed analysis. This is because ISR uses more routing parameters than other. TSR only consider traffic density but not the node mobility. Also, reply and acknowledgement messages can create delay in communication. BBPR need RSU for routing, which cannot be present anywhere, due to which its performance is the worst. Lastly, the applications. VANET has a wide range of applications. Here you can see many applications of VANET. VANET can be used to control traffic and management applications like road congestion, weather information, or route navigation, or it can be used for entertainment purposes, or it can also be used for the safety like lane changing or emergency braking system. Here is a safety-oriented application. When the accident happens, other vehicles receive the warning about the accident, which vehicles can continuously broadcast the accident warning to the approaching vehicles to warn them in advance, which you can see here. Another application is emergency vehicle warning. So when the emergency vehicle is approaching, it can broadcast a warning to the vehicles present in that road. And after receiving that warning, vehicles can move out of its way in advance to make a way for the emergency vehicle. This can help a lot if the patient is in critical condition, and this can even save his lives, which is the main purpose of VANET. Here are the references of the source material of this presentation. And that's it, guys. I hope you all enjoyed the presentation and learned something from it. Thank you for listening to me.